All right, so with chapter 10, what we're going to do is start looking at gases and see the relationship between different quantities such as pressure, volume, and temperature, how those affect gases, and then just a whole bunch of different types of calculations we can do with gases. And with the gases, if we're looking at the planet Earth, the atmosphere, of course, is going to be composed of gases. And with the atmosphere itself, you can see it's about 50 kilometers there. And primarily it's going to be nitrogen. So almost 80% of it's nitrogen, about 20% oxygen, with a small amount of other gases there. Argon will be about 1%, as we can see here, in terms of the volume. And then there is just a small amount of, and not just these three gases here, but a small amount of just a whole bunch of other things there. So we can see carbon dioxide, even though it has a relatively big impact in terms of global warming. Same thing with methane. That's why if you can reduce fossil fuel consumption, if you can reduce meat consumption and other animal products, if we reduce the amount of livestock that produce methane, we could help reduce the global warming as well. And then with it, we've got the mole fraction. And with the mole fraction, this is just going to be in terms of the total moles in the atmosphere, how many of them are nitrogen, what percentage of them are oxygen. And you can see these are actually going to be the same numbers. So we'll see as we go through why that's going to be. And again, the only real difference here is just where that decimal is. So with the fraction, we just have it 2 over, but we'll see why the mole isn't going to really be dependent on what gas it is in terms of how much space it takes up. It's simply just going to be related to how much there is. And with these gases, we do have a set of properties. So we say that gases are going to expand to fill the container they're in. So that's why if you had a balloon filled with some gas and you pop the balloon, that gas isn't just going to stay in the volume it was while it was in the balloon. It's now then going to expand to fill the entire volume of whatever that container is. So it could be the room. If you think about a car, it would then fill the car itself. So it's just going to be whatever that container is. Those gas molecules or gas atoms in some cases are just going to spread out to fill that volume. And then with these gases, unlike that's also unlike the liquids and solids, this expanding part. But also unlike the gas and solids, we'll see that they're going to be highly compressible, meaning that we can change the volume of these gas samples. So if you just think about a balloon again, we have a balloon on top of a mountain and then walk all the way down to sea level. Now we're going to have a different amount of air pressure, and we're going to see the volume of that balloon is going to change as well. So with these gases, we can squeeze them essentially. That's what compressible means. So we can change the volume of them with changes in pressure. Whereas liquids and solids, in some cases, may have very, very, very small changes with pressure. But with the gases, we're going to have much, much larger changes there. So if you've ever worked with gas cylinders, for instance, the gas in that cylinder is extremely pressurized. That's why it can actually fit into that volume of the cylinder. But then if we release that pressure, now it just escapes, and it's going to fill the entire volume of whatever room it may be in. Just because these gases will be compressible, they will be able to expand. And then similar, if we've got multiple gases, then they're just going to mix together for the most part. In some cases, we can see there will be differences in density. So sometimes if we've got a gas that's heavier than air, it'll kind of just sit on the bottom. But for the most part, we're going to see these gases just fully mixing. And then, like I said, the things that we're going to be able to examine with these gases are the relationship between these three properties, and how if we change the temperature, how that's going to affect pressure or volume if we hold the other constants. We'll be able to see how these samples are affected by the changes in these three properties. We'll see other things, such as the amount of gas as well. When we look at the ideal gas law, there'll be a couple other pieces instead of just pressure, volume, and temperature. But with pressure, just to make sure everybody's on the same page, if we just think about what pressure is, it's just going to be some amount of force over a given area. So when we're thinking about atmospheric pressure, what we're essentially thinking about is just how much the force of the air getting pulled down by gravity, how much pressure do we have in that case? And we can also think about it in terms of a balloon. So now the reason this balloon, once we put the air in it, the reason it starts to expand is because we're going to have pressure. We're going to have forces of those molecules. Essentially, they're going to be kind of zipping around, and then they'll continuously just hit the outside of this balloon, and that's what's going to keep it expanded. That's what's going to keep it with that full shape it has here. It's just going to be the pressure from those gas molecules moving around, just hitting the sides of the balloon. And again, that's still going to be related to the force per the given area. So if we think about it, if we increase, and we'll see this as we go through, if we increase the speed of these gas molecules, now they're going to be hitting with a with more force. So if we've got a hotter gas, we'll ultimately see the balloon's going to expand. Or if we have a larger balloon with the same amount of force, now we'll just have a lower pressure. So as we increase the volume, we'll see that the pressure is going to decrease, and we'll actually apply or assign terms to those properties or relationships. But what we've got here is what's known as a mercury barometer. So it just measures pressure, air pressure. And the way it works is mercury, one of the two liquids at room temperature in terms of the elements, bromine being the other. But what we can do is essentially just fill a little pool of mercury, and then have a thin glass tube in it. And then with the atmospheric pressure, like we saw on one of the previous slides, it's essentially just how much is that air pushing down. So there's going to be a force from that air pressure. And then because of that, we're going to see the mercury gets pushed down, but then that forces some of it to get pushed into the pipe here. And the amount that mercury rises, sometimes we measure it in millimeters of mercury. Less commonly, we see inches of mercury. But the amount that mercury rises is going to give us an indication of the atmospheric air pressure. So with the higher the air pressure, the more force we have pushing down, just the higher this mercury is going to go. So with it, we've got, like I said, millimeters of mercury, inches of mercury, 1 atmosphere, 760 torr. So there's going to be a whole bunch of different units that we can use for pressure. So Pascal is going to be another one. So PA for the symbol, bar will be another one still. And then with pressure, normal atmospheric pressure at sea level, we just assign as 1 atmosphere. So if we're at sea level, regular atmospheric pressure would just be that 1 atmosphere, because if we think about it, if we're at sea level, we've got a full atmosphere above us, so that's why we're referring it to 1 atmosphere. And then that's going to be equal to 760 torr, which is the same number, but just a different unit with millimeters of mercury. So if we know the torr, if we're converting to millimeters of mercury, we don't really have to even do any math. It's just going to be that same number. We'll just switch the unit. And then the final one, 101.325 kilopascals, or kilo just means 1,000. So we could move this decimal over 3 and just have 101,325 pascals. So with it, we can see some of the relationships here with those different units. So atmosphere, and then we can see how all of those are just related. So if we wanted to practice with these, we could do that with a few examples here. So 0.357 atmospheres, we want to convert it to torr, excuse me. So if we go back and find the relationship, 1 atmosphere is equal to 760 torr. So if we know the number of atmospheres, one of these is equal to 760 torr. We would be able to just multiply by 760. And that's why if you want to practice with these, just go ahead and kind of pause it, give yourself to work through. With these, since they're just unit conversions, I'm not going to actually go through and show how to set them up. But I will give the answers in just a second. So if you want to work on these on your own, just give yourself a second to jot them down. And then you probably want to go back to the previous slide just so you can see those unit conversions themselves. But with them, if we've got 357 atmospheres, or 0.357 atmospheres, excuse me, 1 atmosphere is equal to 760 torr, which means we're going to have 271 torr. So we'll want three sig figs because we got 3 sig figs here. So it should be 271. With the, and I can write these down, I guess. So 200, oops. So 271 torr. With the second one, kind of the same deal, just now we're going in reverse. So rather than multiplying atmospheres by 760 in order to convert it, now we're going to divide by 760. So we're going to get a very small number in this case. What we're going to have is 8.7 times 10 to the 5th, or 10 to the negative 5th, excuse me, because we're going to be dividing by 760. And then with the final one, this one is going to be a little bit different. In this case, we're going kilopascals to torr. So I'm going to clear this for a second just so we can go back to the previous slide. But kilopascals to torr, so if we hop back, if it will allow me, there we go. So kilopascals, 101.325 kilopascals is equal to 1 atmosphere. 760 torr is equal to 1 atmosphere. So we can really relate torr in kilopascals directly here. So 760 torr is equal to 101.325 kilopascals. So when we look at this one, we'll want to take 147.2, and then we'd have 101.325 on the bottom of our dimensional analysis, 760 on top. So for the third one here, we would just want to get, there it is. We want 4 sig figs since we've got 4 sig figs and 147.2. So we would just want 1104 torr here. But again, with those, they were just the dimensional analysis there. So if we use those unit conversions, we can just focus on the units and link those with those together. Okay. And then with the practice example here, kind of the same idea. So this is looking at the atmospheric pressure in the eye of the hurricane from Hurricane Katrina. So in 2005, New Orleans got hit, and other areas, but New Orleans in particular got hit pretty bad, got hit very bad by the hurricane. The levees were not properly rated for a storm of that quality, so it wound up really devastating that area. But with hurricanes, remember, we got high winds, a lot of rain on the outside, but we've got the eye of the hurricane, where it's sort of the calm of the storm, where it's going to have very low pressures. So what we're going to see, or what we did see with the Hurricane Katrina, is that the atmospheric pressure in the center of that hurricane was just over 90 kilopascals. So if we want to convert these to atmospheres or millimeters of mercury or torr, we can do the exact same thing we just did on the previous one. So again, since these are unit conversions, I'm just going to give the answer. So if you want to pause it so you have time to work on it on your own, you can. But just to make sure that you get the correct answers there, I'm just going to put the number under the unit. So 1 atmosphere is going to be equal to 101.325 kilopascals. So if we had 90.2 kilopascals, we should have just a little under 0.9. So when you do the conversion to atmospheres, what we're going to see is 0.890 atmospheres there. So I'll do that and I'll change the color so we can see what those units go with. So for the second one, millimeter of mercury, what we're going to see is 101.325 kilopascals is 760 millimeters of mercury. So we should have less than 760 because we've got less than 101.3 kilopascals. So what we're going to see is 677. And then we'll actually see the exact same thing for torr because the relationship between those is going to be identical. So 1 millimeter of mercury is equal to 1 torr. So if we had 677 millimeters of mercury, we've just got 677 millimeter torr there. Get the units all jumbled up. And with it, we'll see throughout the different examples, we'll have a whole bunch of different units. So we'll have to get kind of comfortable with those conversions. But looking at what we have here, this is going to be known as a manometer. And it's used to measure the difference in pressure between two systems. So with this one, the atmospheric pressure, and then the pressure of whatever gas we put inside of the manometer. And the way it works is the atmospheric pressure is going to push down on the substance in the manometer itself. So it could be mercury. And then the gas in the manometer is going to do the opposite. It's going to push on the other side. And then based on that pressure, or based on the difference in those pressures, we'll see a different height here. So with the one it's showing now, the pressure in the vessel is going to be greater than the atmospheric pressure. So that's why we're seeing the liquid just get pushed higher up on this side. The force from this gas is going to be stronger than the force from the atmospheric gas, and that's why we see it get pushed in that direction. And then with it, we could look at the difference here. So we could have millimeters of mercury, for instance. We could measure the difference in height here and get ultimately get the pressure in the gas based on the atmospheric pressure, and then based on the difference between those two. So again, if we're measuring this in millimeters of mercury, for instance, and then we know the atmospheric pressure in millimeters of mercury, we can determine what the pressure of this gas in the vessel is going to be. And then sometimes you'll see slightly different setups with these ones. So when the pressure is really low, typically it's going to use a closed end manometer. Whereas when we've got relatively higher pressure, so something around 1 atmosphere, that's where we'll see the open-ended manometers. And just so you can see it, in this case, if we had the opposite occur, so now the atmospheric pressure is pushing down on the manometer with more force than whatever gas we have in here. So pressure of the gas is less than pressure of the atmosphere. That's why we see it get pushed in the opposite direction. If it was exactly equal, then we would have equal, so in terms of height, if they were exactly equal, then we would have the same pressure in the vessel versus the atmosphere. So we just want to kind of think where that liquid's getting pushed and what that means for the relationship between the atmospheric pressure and the vessel there. So with a question like sample exercise 10.2, on a certain day, the barometer in a laboratory indicates that the atmospheric pressure is just a smidge over 1 atmosphere, so just a little over 760 torr. And then a sample of gas is placed in the flask attached to an open-ended manometer. A meter stick is used to measure the difference in height in the mercury. And on the open-ended side, we're going to have a height of 136.4 millimeters. And on the opposite side, so the side that's getting pushed by the gas in the vessel, we've got a height of 103.8. And we ultimately want to determine what the pressure of this gas is going to be in atmospheres as well as kilopascals. So if you want to work on this one on your own, go ahead and pause it. But what essentially we're going to be doing is using this equation. So we already know what the atmospheric pressure is. We know what the pH is, pressure of the height difference. So we can use those to determine what the pressure of the gas is going to be. But since this information is given in torr and millimeters of mercury, again, those are identical. We just have to change the unit, but the number stays the same. We can get the pressure of that gas pretty easily. But then since we want it in atmospheres and kilopascals, we would then just have to go one step further and just convert it there. So if you want to practice on that on your own, you can. But this is going to be P of the atmosphere, so ATM. And then with the height difference, pH, what we're going to see is it's going to be 136.4 minus 103.8. So we're ultimately going to wind up with what, 32.6. And then with it again, we can just change the units of either of these. We can change this one to torr, or we could have changed 764.7 torr to millimeters of mercury, but we just want those to match up. And again, it's the same number, just different units, so it doesn't matter which one we change. But once we have that, then we can use our relationship with these different pressure units. So with atmosphere, when we have these two together, we're going to wind up with 797.3 torr or millimeters of mercury. But we want atmospheres and kilopascals, so 793 or 797.3 torr is going to be equal to just a little over 1 atmosphere. And we've got 4 sig figs in our initial pressure value, so we'll want 4 sig figs in our answers here. So we should wind up with 104.9 if we have it in atmospheres. Or with the kilopascals, again, just doing our dimensional analysis, convert one unit to the other by setting up our parentheses. We cancel out the units by having them in opposite spots. So something in the numerator gets canceled out by something in the denominator. But with this one in kilopascals, 101.325 kilopascals is our atmospheric pressure at sea level. Or our normal atmospheric pressure at sea level. So what we'll see, since we're a little bit above that, is we'll have a pressure in kilopascals of 106.3 there. Okay. And then with these gases, like I said, we can use pressure, temperature, and volume to relate these. And when we're looking at a constant volume, or constant temperature, excuse me, gotta make that. When we're looking at a constant temperature, we're gonna see the pressure and the volume are inversely related. So with it, we can look at the picture in a second, but if you just think about a balloon, if you squeeze a balloon, it's the same amount of gas inside that balloon, whether we squeeze it or not. But when we squeeze it, now we're decreasing the volume, we're forcing all of those gas molecules closer together. We're gonna see the pressure is gonna increase. Whereas if we take a balloon to the top of a mountain, so walk it all the way up to the top of a mountain, we're going to see the atmospheric air pressure is going to decrease throughout. So we would then see the volume of that balloon expand. So we're going to see the pressure and the volume are going to be inversely related, meaning as one of them goes up, the other is going to go down. But again, this is if we're keeping the amount of gas constant at a constant temperature. So if we change the temperature and the amount of gas, we're going to have other things going on. So with these different relationships, we're only changing those two things. So we're focusing on pressure and volume here, while everything else is going to stay constant. And what this is referring to is what's known as Boyles Law. So with the picture here, what we're going to see is we've got some amount of atmospheric pressure pushing down on this. And then if we have some volume here, so 60 milliliters, if we then add more mercury, we decrease the volume, but we still have the same amount of gas on this side of the manometer. But now we've got half the volume, so we're going to have twice the pressure. And when we're looking at the relationship between these two, so again, temperature and then N, so T for temperature, N for moles of gas, because we're keeping both of those constant. What we can see is pressure times volume then is just going to be equal to some constant based on the temperature and the amount of gas we have. But if we're keeping those constant, what we can do is set up a relationship where P1, V1, meaning our initial pressure and our initial volume, are going to have to be equal to our second pressure and our second volume. So as we change the pressure here, we can determine how that volume is going to have to adjust accordingly, or vice versa. If we change the volume, we can see what that pressure is going to have to be. And if we look at the graphs here, what we're going to see is as the volume decreases, the pressure is going to go up. or we can think about it the other way. As we start to squeeze this more, we have the volume go down. And then what this allows us to do is take the inverse of pressure. And then what we're going to see is a straight line. Where K will just be, or where the slope, I should say, is just equal to K, which is just going to be that constant based on the temperature, based on the amount of gas there. So as we change the temperature, as we change the amount of gas, where exactly this line is going to be will change. But the relationship we see won't. So we'll still see as pressure goes up, volume goes down, or vice versa. Oh, I never realized that. If anybody's watched Brooklyn Nine-Nine, there's Charles Boyle. I never realized that he's kind of got both of those names there. But with Charles' law, now what we're going to see is that the volume of a fixed amount of gas at constant pressure. So now we're keeping pressure constant. We're keeping the amount of gas still constant. So now we're going to be relating temperature and volume. What we're going to see is that these are directly related. So as one of these goes up, the other is going to have to go up if we're keeping pressure and amount of gas the same. So that's why if you've ever heat up a gas sample, air pressure on the outside is going to stay constant. So it's just going to continue to expand against that force. And like I said, as one of them goes up, the other is going to go up. So that's why when we look at the graph here, we're going to see that exact relationship. And an example of this could be something like your car tires in the wintertime. So in the summer or the fall, you may have fully inflated tires. But then in the wintertime, when the temperature goes down, we're going to see kind of going in the backwards direction here. As this temperature goes down, the atmospheric pressure on the outside is more or less the same. The amount of gas in those tires, unless you have a leak, is basically going to be the same. There will be some loss there, but it's basically going to be the same amount of gas, basically going to be the same pressure on the outside. So what we're going to see is as the temperature goes down, the volume of that gas is going to go down as well. And that's why the tires in wintertime tend to get slightly deflated. And then with the concept of the mole, we talked about Avogadro's number, 6.02 times 10 to the 23rd. What we're going to see with these gases is what's known as Avogadro's law, just meaning that the volume of a gas at constant temperature, constant pressure is going to be directly proportional to the number of moles of that gas. So as we have more gas at a constant temperature, constant pressure, that gas is just going to occupy more and more space. And with it, you'll see that there's no, in this equation, there's no real spot for what gas in particular we have. So there's nothing for the molar mass or anything like that, nothing to specify H2 gas versus oxygen gas versus water vapor. And that's why if we think back to one of those earlier slides where we had the composition of the atmosphere, the mole fraction and then the volume percentage were exactly the same. We just moved the decimal over 2 because these gases, regardless of what substance they are essentially going to occupy the same amount of space if they're under the same set of conditions. In reality, there will be slight deviations with that. So we'll actually see what's known as ideal versus real gases, where there is some differences in the behavior of real gases, but we'll see a lot of the similarities there between gases, regardless of what type of gas it is. Okay. And then with this next one, the pressure of a fixed quantity of gas is directly proportional to the temperature. And then with this, you'll notice there's a very similar relationship. So as pressure and temperature, as one of those goes up, the other goes up. So if we're looking at how we can relate the change in pressure and temperature within one sample, assuming again we're keeping the amount of gas constant, what we're going to see is P1 over T1, so the initial pressure over the initial temperature, is equal to the final pressure over the final temperature. And that's going to be very similar to what we saw with Charles' law. So in this case, we've got volume over temperature for Charles' law. Now we've got pressure, but they're going to be very similar. And that's why we can actually use them and combine them into what's known as the combined gas law equation, which basically just takes all of those different laws we talked about, and as it would suggest, combine them into a single equation. So P1 V1 over N1 T1, pressure, volume, moles of gas, and temperature of those initial conditions is going to be equal to the pressure times the volume divided by the amount of gas divided by the temperature for the second set of conditions. And again, it's kind of just a combination of all of these things. And then when we combine them, we can see that the volume is going to be directly related to the amount of gas times the temperature over the inverse pressure. And that's kind of, if we just focus on one side of this, we can solve for pressure and kind of see that similar relationship there. And then with that, that's going to then give us this ideal gas equation. So you may be familiar with PV equals nRT. We lost a symbol here with just the relationship, so directly related. But what these stand for are, now if we're looking at just a given set of conditions, so rather than seeing how a gas sample changes from the initial to the final conditions, now we're just looking at a gas sample under one set of conditions, and we can relate the pressure, the volume, the amount of gas, and the temperature to each other with this equation. And what R is going to represent is just what's known as the gas constant. And this R is actually going to have a whole bunch of different values depending on what units we have for these other pieces here. So if we look at it, P is still pressure, V is volume, N is moles, T is temperature. It's going to be critical that we always have temperature in Kelvin. Of course, in science, we never use, or at least in this course, we never use Fahrenheit. I think Fahrenheit does make sense for environmental conditions, for even biological organisms in some cases, if we want to see a change in temperature. It's got a slightly larger scale, so it makes it a little bit easier to see changes in temperature. But with chemistry, we're pretty much never gonna use this Fahrenheit. And then with Celsius, even though it's the same scale as Kelvin, Kelvin can only go down to 0. So we had it on one of these previous slides. Not that one. Here. So in this case, we've got temperature and negative, or temperature in Celsius, but we can see we can have a whole bunch of negative temperatures in Celsius. Whereas Kelvin, what they're representing right here, starts at 0 and then just goes up at the same scale. So since Kelvin can never become negative, that's what's going to be. That's why we're going to use it in these gas equations. If we plug in a negative Celsius value here, it's just going to completely throw everything off. So the Kelvin is what we're going to want to always make sure we use for the temperature. N is always going to be moles of gas. And then in terms of what we have for pressure and volume, those could actually vary. So moles and Kelvin always have to be just those units. But pressure and volume, we could have in a couple different things. And that's why we can actually have a whole bunch of different values for R. But if we're looking at what we have here, pressure in atmospheres, volume in liters, that's why when we look at the R value, that gas constant, that's why we have liters atmosphere as our unit there. And then with this, just because it is a kind of weird unit here, just to show what that is, that's liter times atmosphere on the top of our unit. So similar to like grams per mole, we've got a fraction for our unit. Now we've got the same thing, it's just we're multiplying two things on the top and the bottom. So we've got liter atmosphere mole Kelvin, because when we plug in R now, we've got mole, so that will cancel mole. So N is mole, so that'll cancel the mole on the bottom of our unit here. Temperature is in Kelvin. Cancel that as well. And now we're just left with liter atmosphere on the right-hand side. And again, that's going to be what we have on the left for pressure and volume here. But if we did have pressure and volume in different units, we would just need to use a different R value in order to make sure that our units match up, make sure that our calculation is ultimately going to work. Oops. And then with the R, like I was saying, depending on what unit we have, kind of a whole host of actual numbers for it. So the one that we'll use most commonly is liter atmosphere mole Kelvin, or liter atmosphere over mole Kelvin, I really should say. So 0.08206. But if we had torr instead of atmosphere, 1 atmosphere is 760 torr, so we're going to see a different number. We're going to see 62.36. Or if we had meter cubed Pascal, now we have 2 different units there. So we're going to have 8.314, which is going to be the same thing as joule per mole Kelvin there. So with these, just make sure that whatever we're plugging in for R, the units on that universal gas constant are going to match whatever we have for the volume and the pressure on the other values, other quantities in that equation. But again, with the bottom, we'll always have mole Kelvin because we always want to make sure we've got temperature in Kelvin for these, and then mole is just how we're going to always keep track of these different substances. Okay, and then with it, that'll be where we wrap up the first video here, because the next one is just going to look at a whole bunch of different calculations. So this is kind of just showing us those the basic pieces. With the next video, we'll look at a whole bunch of different practice problems and actually see how we can apply all this information.